Hi everyone, my name is Dries Heylen. I'm a Belgian researcher connected to Hasselt University and VITO. I will guide you through my poster entitled Evaluating the Frequency of Multi-omics Longitudinal Data Collection in the Perspective of Chronic Disease Development. To start with, what's the incentive of this research? Recently, frequent longitudinal measurements of multiple omics data are emerging as new technical advancements for the in-depth analysis of molecules in small blood volumes are appearing. This makes the sampling process less disruptive for patients and can allow the routine usage of such measurements in clinical practice. We aim to prove the surplus of these highly granular measurements for assessing disease development, since applications that prove this are currently lacking. So, we gathered a unique combination of molecular data. From the one hand, we at VITO ran the IM Frontier cohort study, which is a longitudinal multi-omics study in which a broad range of omics data are repeatedly and with high frequency collected at different time points throughout an entire year. This is indicated by the circle stacks on the left side of the poster. Participants were selected to have no disease diagnosis at the start of the study. Since we want to assess the added value of frequent data collection in the perspective of chronic diseases, we complemented our cohort data with UK Biobank access. The UK Biobank is a large-scale cross-sectional study with data that matches our internal data. Overall, the UK Biobank study serves as the source to identify clear disease profiles in order to let the IM Frontier data thrive in unraveling subtle dynamics as part of intermediate changes between health and disease. For 20 biochemical features that are measured in both the IM Frontier and UK Biobank cohort, it was assessed whether a non-diagnosed IM Frontier individual with an initial high risk for type 2 diabetes that declined throughout the study period shows monthly intermediate changes in a disease spectrum stretching from healthy baseline individuals up to diagnosed individuals of the UK Biobank cohort. This assessment was done by applying the Pareto loss inference method on the combined dataset. Situated on the left side of the slide, you can see the course of a single individual's diabetes risk. This risk is based on the Diabetes Find Risk score, a score that is generally an accepted estimator for the risk on type 2 diabetes. The Find Risk score focuses on things like family history, lifestyle habits, and basic physiological measurements. Since there is a general clear negative trend in this score, indicating a lower risk for the disease at the end of the measurements compared to the beginning, we decided to check how that person's profile, based on the clinical biochemical measurements, behaves throughout the months of the data collection when we place it in a spectrum that includes both healthy as diseased individuals. Overall, we see that the selected person indeed slightly moves away from the yellow dots. These dots represent the clinical profile of a diagnosed diabetes patient. In this proof of concept example, 15 out of the 20 selected clinical measurements are already known to be established type 2 diabetes parameters, meaning that 15 of those are in some way already linked to the pathology of type 2 diabetes, which is an important criteria to keep in mind for similar analysis. We believe the applied tools can help for the presented combination of multi-omics data to evaluate how time-sensitive each data type is with regard to intermediate changes between health and disease. In the next step, intermediate phenotype profiles will be annotated in disease pathways stored in a clinical knowledge graph database. This can help in granularly defining how specific molecules in the human body play a role in disease development.